So today we will be talking about thermodynamics and trying to wrap that particular section up. I'm going to hit the high point and not do the extra stuff that is interesting, but is not really part of the questionnaire or your final. Remember, you have an ACS final, and most of that type of questions on your final is about making sure you understand thermodynamics, not so much about how it applies in the scheme of things, but that's always the interesting part. And then towards the end of class, I will talk to you guys about your midterm and how I'm going to adjust that score so that the average is about 75%. So, and then let you know about preparation because you guys miss a lot of the concepts on that particular midterm, and these concepts are pretty important if you are going to be taking organic chemistry or if you're even planning to do the MCAT. So I'll talk to you guys about that towards the end of class. So please try not to ask me about that because we do have a lot of things to cover in thermodynamics. For lab, you guys have thermodynamics experiment. It's pretty easy experiment, but I want to make sure that you guys understand the equations that you will be using, as well as an activity later on this week. So I want to get through this particular aspect of the discussion so that you'll be ready to answer the questions in the activity. So last time we talked about state functions, and the state functions that you guys were introduced to were enthalpy and entropy. Enthalpy is the energy with respect to the universe, the system, the surroundings at constant pressure. Entropy is not at constant pressure, it's just the degree of disorder or the microstates available for a system or for the surroundings or for the universe, for that matter. Make sure you understand the terminology that we are using in terms of the universe, the system, and the surroundings, because we're always going to try and refer to one of those, especially the system, when we talk about state functions, okay? So in this discussion today, we're going to be talking about the third state function, actually the fourth, because the other state function is energy. That's a state function. But the state function that we are going to be discussing today is free energy. So free energy is about spontaneity. Remember, hope you can remember from last Monday that the second law of thermodynamics says spontaneous process are always going to be the process in which leads to greater entropy. The greater the entropy, the more spontaneous it is. Of the universe, that is, the entropy of the universe. Entropy is always increasing. If the entropy is zero, then you're at equilibrium. If the entropy is negative, then the reverse is the spontaneous process. So please remember that because it's the heart of the discussion for today. So we're going to be looking at, first of all, delta S of the universe positive is a spontaneous process. The problem with delta S of the universe is that it's with respect to delta S of the system plus delta S of the surrounding. And the problem with that equation is that you have to monitor two different aspects of the universe. You have to look at the system and the surroundings at the same time, and that's very difficult to do. It's much easier to just focus your attention to either the system or the surroundings. It's much better to focus your understanding on the system, okay? That is the process that is taking place. So if we can write the delta S of the universe, which is really the main focus of spontaneity. If we can write the delta S of the universe with respect to the system, then we have we have a game changer in terms of understanding thermodynamics. So what we're going to do is we're going to look at, say, the universe. This is the universe. And we're going to understand exactly how the system and the surroundings interact. Now, remember that if heat is released, then that means if heat is released by the system, that means that the heat is absorbed by the surroundings. And that's what we're going to key on. So the next few discussions here, the next few PowerPoint just kind of puts it in the realm of how we're going to translate the delta S of the surroundings in terms of delta H of the system. Okay, and I'm not going to go through the detail because I just want you guys to just apply the equation, which is really the important equation. So let me clear this, okay, and tell you that remember that when heat is released, then generally that means that the entropy also increases. So that means the delta S of the surroundings is proportional to the delta H of the system. That is, the entropy of the surroundings is going to be related to how much heat is given off by the system. And that's what we see right here, okay? That's what that discussion is right there. And so we can say that the heat is going to be related to the heat of the system, that is the heat that the system releases, but it's proportional to the entropy that the universe, the surroundings, takes place. Anyway, we're also going to see that it's inversely proportional to the temperature. And this discussion tells you why it's inversely proportional. Inversely proportional means that it's divided by, if you want to change the equality. So we're going to use this relationship right here, that the delta H of the system, that is the heat that is released by the system, divided by the temperature, okay, that gives you an indicator of how much heat is released, because temperature is an indicator of kinetic energy. It's an indicator of heat, is proportional to the entropy that the surroundings get. So we can actually use this relationship right here so that we can express delta S of the universe in terms of the system for the delta S of the system, but also system in terms of delta H. And now we can monitor the increase in entropy of the universe with respect to the system. And that's all that we are trying to get to in this relationship. So they give you a roundabout way, but the most important thing is this relationship right here. Okay, this relationship right here. Now we have the universe, because remember, when it's positive, it's spontaneous in terms of the system. Okay, we just make this substitution right here. We just make that substitution right there. That's not quite the equation you need to remember, because we're going to simplify it even further, okay? So just to go back, delta S of the universe positive is the bottom line in terms of spontaneity. When the delta S, when the entropy of the universe increases, that's a spontaneous process. That's the bottom line in terms of second law of thermodynamics. So that's the equation that we are going to be using, okay? That's the equation that we're going to be using, and it's indicated in this slide. So we can take this equation and simplify it by just multiplying this whole thing, change my pen, by t, negative t. And when we do that, we get this. Now this right here is close to the equation that you need to write down, because it's really important. It not only expresses the delta S of the universe in terms of the system, but it frees up delta H in terms of just the heat that is exchanged. Okay, now this equation right there, a guy by the name of Willard Gibbs, recognized that that could be a new state function. And what he did was he called that new state function free energy. And we call it delta G system at this point. So Willard Gibbs, he was, I believe, from Yale. He was an engineer, but he recognized that. And we have this new state function, and we have this is just some background on Willard Gibbs, okay, that he was an engineer, but he contributed a lot to thermodynamics. But he gave us this new state function, delta G, which is really called Gibbs free energy. Later on, you're going to understand why it's called free energy. What's so free about energy? But that's what we're going to be talking in the later slide. Now we have this delta S of the universe in terms of delta G, and we can simplify that equation to the following. Let me take you back again. Remember that when the delta S of the universe is positive, because there's a negative in front of that, that means delta G, spontaneous, is negative. So negative delta G is a spontaneous process because of that negative T delta S. Okay, so again, negative less than 0, it's spontaneous. When it's equal to 0, that hasn't changed. That's equilibrium. And when it's greater than 0, that would indicate that the universe is less than 0. Remember, they have opposite sign. Order in the universe is not a spontaneous process. Delta G being positive is not a spontaneous process. So the reverse is a spontaneous process. So the bottom line is, this just tells you through a mnemonic device that when you're negative, the forward direction is the spontaneous process. When you're positive, the reverse direction is the spontaneous process. It's like Q in equilibrium. And when you're at 0, you're at equilibrium. Okay. So this is the main equation that you guys need to remember. Delta G, free energy, is equal to delta H minus T delta S, And if this is the system, then this is the system, and this is the system. If it's the surroundings, then delta G will be surroundings, delta H will be surroundings, delta S is the surrounding. But it's much easier to monitor the system, okay? So this is basically what we have in terms of this equation. And again, the super zero here tells you we are at standard state. Free energy also is a reference scale, okay, like enthalpy. Enthalpy, there's no absolute, unlike entropy. Entropy, absolute zero, pure crystalline material has an entropy of 0 at minus 273. But for enthalpy, it's going to be, the 0 point is for the pure chemical at 298 1 atmosphere. Okay, so go back to the last lecture and look at the conditions for standard state. Well, we have standard state conditions for free energy as well. And that would be, if you guys have a question, just unmute yourself, okay, so that I can hear you. But in this particular case, what we're doing again is introducing you to the notation so that you understand what we're referring to. Okay, so the super zero tells you it's at standard state. You already know it's at 298 1 atmosphere. That's what you should know it's going to be for the conditions that we talked about last time. Okay, to calculate the free energy from, say, the appendix, because we've tabulated the free energy for many chemicals, it's the same as what we did for entropy. It's the same as what we did for enthalpy. That is products minus reactant. The moles, this right here represents the moles. The sum of the moles of the products minus the sum of the moles of the free energy of the reactant. That's your delta G of the reaction. Products minus reactant. It's always final minus initial in this particular case. So let's take a look at this example. First of all, let's just study this example and make some predictions. And that's what you guys should be able to do based on what you've learned in your chemistry so far. Okay, this right here is methanol, CH3OH, okay, with oxygen, and it's producing carbon dioxide and water. Right away, you guys should know this is a combustion reaction. How do you know it's a combustion reaction? Because oxygen is a reactant, carbon dioxide and water are the product. So you guys should have learned that in general chemistry. Okay, you take a hydrocarbon or a fuel in the presence of oxygen, give it a little spark, and it produces a lot of heat, a lot carbon dioxide and water. Okay, so if it produces a lot of heat, you already know without even doing any calculation, the delta H in this particular case is exothermic. Exothermic means delta H is negative. Okay, heat is released, that means heat is a product, delta H is negative. If it was endothermic, delta H would be positive. So right away, I know the sign of delta H. The other thing you should know is the sign of delta S. And we're just looking at the system at this point. We're looking at this reaction. And here you can see that, yeah, they're gas going to gas. This is not a balanced equation. If we balance this equation, we will see that we would need four hydrogens. We've got one carbon, we've got 2, 4. We need 2 oxygens right there to balance the equation. Okay, don't ever assume that an equation that's given to you in a problem is balanced. Always double check it. This is especially true when we get into electrochemistry next time. Okay, so this is a balanced equation. So gas going to gas, that doesn't tell you anything about entropy. But 3 moles of gas going to, in this particular case, 3 moles of gas, again, that's basically a wash, okay, in terms of the moles of methanol going to the moles of product in this particular case. So let me just, oops, it's not really balanced. I forgot. We've got 4 oxygens in this place right here, but we've got, let me clear this up. Okay, let me balance this again because I forgot there's an oxygen over here. So 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens. Here we have 4 oxygens in this side, but here we have a total of 3 oxygens. Okay, so we need a total of 4. So the way we do that is we make this 3 halves. When we make that 3 halves times 2 is 3, 3 plus 1 is 4. Now our oxygen is balanced. To get rid of that fraction, we multiply everything by 2. So when we have a balanced equation, the coefficients is the following. Yeah, make sure you balance your equation correctly. This is going to be 2, this is going to be 3, this is going to be 2, this is going to be 4. Okay, so that's the balance equation. And now you can see in terms of entropy what's going on. The gas are the same, but the moles of products are greater. We've got 6 moles of products here. We've got 5 moles of reactant there. The moles of the products are greater, the entropy increase. So in this particular case, delta S is going to be positive. So right away, before we even do this reaction, we know that delta H is negative and we know that delta S is positive. The thing that you will see in your activity on Wednesday is the following. You guys are going to be asked to solve problems like this. And what you need to do is to figure out what the values are. And you do that by looking in the appendix. Okay, you look in the appendix. So the question, can you repeat how you knew delta H is negative? You guys know that when you burn something, heat is generated. If heat is generated, that means heat is released. If heat is released, that means it's an exothermic process. Okay, you learned that from thermochemistry. When heat is released, it's an exothermic process. So that you should know from the top of your head. Let me see. Yeah, all combustion reactions are going to be exothermic reactions. And then in terms of the entropy, you guys need to look at the phases and the moles of the product, as well as the complications, look at the things that we talked about last time, okay, to give you an idea whether it's positive or negative. And we're not doing any numbers here. We're just using what we know about these chemicals. So what you guys will be asked to do, and these are pretty straightforward problems. The key is to make sure that you look up the correct value in the appendix or in the back of your lab manual. So we're going to look up the delta H of the chemicals. We see that the delta H of the chemicals, and this is going to be in kilojoules because delta H is expressed in kilojoules, is minus 393.5 and 241.82 for water and carbon dioxide. We have to multiply this by 2 because of that, and we need to multiply this by 4 because of that, okay? For oxygen at standard state, it's found at standard state as a gas, so that's 0. Okay, that's 0. You should know that. And then for methanol, that's 201.2, and we need to multiply that by 2. We do the same thing, and when we do that, products minus reactant, we get negative 1,351.88 kilojoules. Makes sense that it's negative, and it's a big number because there's a lot of heat that's released. Negative meaning it's exothermic. Now we do the same thing for entropy. We look up those values, and those values are going to be found in the appendix. And make sure when you do this, this is a common mistake that I see a lot, okay? When you look up the values, you got to make sure that you use the values for the correct phase, because what you will see is that there's going to be water solid, water liquid, and water gas, because those all exist under some conditions. If you use the wrong value, you're going to get the wrong answer. So you need to look up water gas, because that's the phase. That's why paying attention to the phase is important in thermodynamics. So the problem with delta S is that the units are joules, okay? That's another mistake I see a lot. You forget that the units for delta S is joules. And so when you're putting it in the equation, delta G equals delta H minus T delta S, you're forgetting to convert the entropy value to kilojoules, okay? If you forget that, your answer is going to be off. And you see that a lot, and I've still noticed that you guys are doing the same mistake. You see that in when you're using the Arrhenius equation. In the Arrhenius equation, the equilibrium, the kinetics rate constant is equal to A, that's a pre-exponential factor, e to the minus EA over RT. R is in joules, but EA is generally in kilojoules. Okay, so you've got to make sure that your units are always consistent with each other. Otherwise, you're going to be off by 1,000. So in this particular case, this is going to be in joules. And then again, you need to multiply it by 4 here, multiply it by 2 here. This is not 0 because remember, oxygen will be 0 at minus 273. At 298, it's not 0. Okay. So that's going to be given, it's going to have a value for you. And you, again, you do products minus reactant. And when you do that, you get positive 92.32. Again, consistent with what we predicted, consistent with what we predicted. The entropy is increasing because you have more moles of product. So there's a greater disorder. Now, the units here are joules per Kelvin. Why is it per Kelvin? Because you need to multiply by the temperature. And the temperature at standard state is 298. So you need to multiply this by 298 to get it to kilojoules, and then, of course, convert joules to kilojoules by multiplying by 1,000. That's important. Now, if you take these two right here and do delta H minus T delta S and solve for delta G, you should get an answer very close to this one right here, products minus reactant. It won't be exact, but it's very close. So there's two ways of getting free energy. One way is to get free energy by delta H minus T delta S. The other way is through products minus reactant for free energy, okay? And so when you do that, you get negative 1379.28 kilojoules. And you should try that. You should plug in 1351.88 minus 298 and 92.32 in kilojoules is going to be 0.09232. Remember, you have to divide by 1,000 to convert joules to kilojoules. And if you do that right there, you should get a number very close to that. It won't be spot on because there's a few assumptions that we really need to take into account, but it's going to be very close. In fact, if you look at activity, I believe 9, thermodynamics, it asks you to do that. So that's really good practice, okay? So the math in those types of problems are easy. You just got to make sure you're using the correct values. Okay, so if you get a problem in which you have to calculate free energy using delta H minus T delta S or products minus reactant, you should be able to do that. In fact, you can even do that if you put it in a spreadsheet so that Excel can do it for you. You just have to code it correctly. But the key in making sure that you don't get those problems wrong, again, when it comes to a multiple choice test, and that's what your final is, okay, they're going to give you choices in which you either they give you the wrong value for the different phases, or they give you they don't convert the joules to kilojoules. Okay, you may understand the concept, but you're going to get the answer wrong. And so you should train yourself in making sure you work through that problem correctly from the beginning and try not to make mistakes that are easy to fix. And for those of you who are going to be doctors in the future, your MCAT's like that, okay? Nothing more than multiple choice, maybe some free response, but if you make the wrong assumptions, you might know the concept, but you're going to get the answer wrong. So please use the fundamentals that you know and always double check your work. Always double check your work in this particular case. So I'm going to shift gears on you right now, okay? I'm going to talk to you guys about the concept of temperature dependency. What exactly is temperature dependency? Temperature dependency has to do with it's spontaneous under one temperature. It's not spontaneous at a different temperature. And there is some temperature when it goes from non-spontaneous to spontaneous or vice versa, that is the switching temperature. The switching temperature is when it's at equilibrium. I'll give you a classic example. Suppose we have a solid, let's take a look at water. And water is a good example because you guys are going to see this example again. If not in the next exam, certainly down the road. If we take a look at water and we look at the different phases of water, water has a solid, a liquid, and a gas phase. Okay, solid ice, liquid water, or vaporous steam, or water vapor. And what we can do is that when we have solid ice and we convert it to liquid water, we need to apply heat. In order to, when we apply heat to the system, that's a endothermic process. So here we say that delta H is positive because in order to get the solid to a liquid, then we have to apply heat to the solid to melt it. When we go from a solid to a liquid, the liquid is more disorder. So we can say that delta S in this particular case is going to be positive as well. Okay, delta S is going to be positive as well. So just understanding the phase change and what happens to water, you guys can predict the sign of delta H and delta S. For a solid going to a liquid, that's an endothermic process. Entropy is increasing. But in the reverse will always have the opposite sign. If delta H is positive in one direction, delta H is negative in the reverse direction. When a liquid goes to a solid, it has to dump off its energy. That way the molecules will slow down and then solidify. And then you guys know that delta S in this particular case is also going negative. It's becoming more ordered. That's not a spontaneous process, but it can be for the system. That, remember, it's not a spontaneous process in terms of the system, but the key indicator is that delta S of the universe is never negative. Delta S of the system can be negative, but not the universe. Okay, that's important right there. So you guys should be able to work through all of this. When a liquid goes to a gas, when a gas returns back to a liquid, you know the delta H for that is positive. It's endothermic. When a gas goes back to a liquid, it has to dump off its heat. That's exothermic, negative. Okay, you know that the delta S for a liquid going to a gas is going to be positive, but a gas going back to the liquid is going to be higher ordered. And then we can also do this. A solid going to a gas, it's called sublimation. Okay, that's called sublimation. That requires energy and vice versa. And why am I doing this? Because this is a good example of how we can change a spontaneous process to a non-spontaneous process simply by changing the temperature. Simply by changing temperature. Now, don't get me wrong. Sometimes changing the temperature doesn't change the spontaneity. Something will always be spontaneous no matter what the temperature. Something will always be non-spontaneous no matter what the temperature. But you guys need to know how to recognize that, and that's what this discussion is about. Okay, so let me go ahead and clear this and talk to you about how to understand this. So we're looking at delta H and delta S. Okay, we're looking at that. And those are the two parameters that is going to indicate the sign of free energy. Those are the two parameters that are going to indicate the sign of free energy. Those are the two parameters that are going to indicate spontaneity or non-spontaneity. Okay, those are the two factors right there. So remember that delta S is in joules. So it's 1,000 times less than delta H. It's a small number from the get-go, in other words. Okay, now if delta H is large and delta S is small, then what happens here is that the enthalpy is going to be the main indicator of free energy. It's going to be heavily weighted on the enthalpy, delta H, because it's large, okay? Delta S by nature, because it's always expressed in joules, is generally going to be always small. But how do we make it large? We make it large by T, right there. When T is large, then this factor, T delta S, becomes important, okay? Think about that a little bit. There's two things weighing on you in terms of spontaneity: the energetics of the system, the disorder of the system. Okay, when the energetics is large, then free energy is going to take on the sign of delta H. Delta S, however, depends on the temperature. Delta S is going to be dependent on the temperature. So when that's large, then T delta S becomes significant. The switching point is when delta H equals T delta S. That's the switching point. And remember that, because there's questions about that type of problem as well. Anyway, let me go ahead and continue with this. Okay, what is the sign of delta H? Delta G, I mean. Okay, well, it's going to be temperature dependent. It's going to be temperature dependent. Let me clear this real quick. Okay, why is it temperature dependent? Because when T is small, then that number is going to be insignificant, and it's going to be heavily weighted on delta H. But when T gets large enough, then this value right here might overtake delta H. So that's where the temperature comes into play. How high a temperature do you need so that this factor becomes important? Well, it depends on delta H. Depends on delta H. Okay, so again, here is a summary of what we have. When we have small temperature, then delta H dominates, because a small number times a small number will be a small number. So that part is negligible. On the other hand, when temperature is large, when this becomes large enough, how large? It depends on delta H. But when it becomes large enough, then this term dominates. And remember, there's a negative in front of that. There's a negative in front of that. That term dominates, and it pushes the free energy to the sign, depending on what the entropy happens to be. Okay, so these are conceptual discussion. Hopefully you understand that. It's basically math. It's basically math, understanding which parameter is important depending on the values of the other. Let's take a look at water again, okay? Because this is really important. We know that solid going to a liquid, the enthalpy is positive, it's endothermic. For liquid going to a solid, the enthalpy, delta H, that is exothermic. So this is the sign of delta H with respect to the different phases, okay? Entropy from a solid to a liquid becomes more disordered, from a liquid to a gas, more disordered, and then in the reverse direction, it becomes more ordered, okay? So in order for a phase change to occur, when we have a phase change, that's at equilibrium. I just want to make sure that you understand that. At equilibrium, delta G equals 0. That's important. And you guys have to understand what exactly is an equilibrium process. When you have a phase change, that's an equilibrium process. When a solid goes to a liquid, that's a phase change. So you can actually do this. Delta G equals delta H minus T delta S. Okay. And let's say we're going from a solid to a liquid. Okay. Well, that's at equilibrium. When we're at equilibrium, this is 0. The question is, well, can we calculate at what temperature this equilibrium happens? Yes, you can, because what we can do is we can solve for this equation right here. We know that's 0, so we can say that delta H equals T delta S. So we can calculate the switching temperature. That right there is the switching temperature. That right there is the equilibrium temperature. Don't forget that, because you will do that a lot of times. When graphite turns into diamond, that's a transition, that's a phase change in terms of graphite going to diamond. You can actually calculate that temperature as well, okay? Because you can look up the delta H and the delta S for graphite and diamond. If you do this for water, you should find that the temperature is going to be about 373 Kelvin. Remember that the temperature is always going to be in Kelvin. And don't forget to convert delta S to kilojoules. Otherwise, you're going to be off. Or convert enthalpy to joules. The units need to cancel, and the only units left, this is in kilojoules. We're going to convert delta S to kilojoules per temperature, Kelvin. So these cancel, and then this goes up into the numerator. You've got your correct unit in terms of temperature, Kelvin. Okay, so this is a very important concept, and you guys will have to use this equation again many times over. That's just something that comes out from this discussion. You can figure out the equilibrium temperature for a system. Okay, let me clear this real quick. So this is basically that discussion right there. It's that discussion right there. Okay. So let me go through this again in terms of spontaneity, depending on the size of T. Let's take a look at this real quick. So here we're looking at delta H and delta T. Delta H minus T delta S. So let's say that we have, in this particular case, delta H of negative and delta S is positive. Okay, excuse me for the format. The format is messed up on this. This is 2 over, but the negative refers to delta H and the positive refers to delta S. Think about that. Delta H negative, exothermic, spontaneous. Okay, spontaneous. Downhill reaction, reaction that always releases energy, that's spontaneous with respect to energy. It's downhill. Look at delta S, positive. Increase in chaos, increase in randomness. That's also spontaneous. The fact that there's a negative in front of that makes this a negative T delta S. So you have a negative delta H and you have a negative T delta S. A negative and a negative will give you a free energy that's always negative. It's always spontaneous, no matter what the temperature. No matter what the temperature. So when delta H is negative and delta S is positive, there is no temperature that will make it non-spontaneous. It's always spontaneous. It's always spontaneous. Think about it this way. When energy is being released and chaos is occurring, those are 2 favorable processes. It's always spontaneous. One is not competing against the other. Okay? Look at the other scenario. What happens when it's an endothermic process? So what you need is to apply heat, add energy to get that reaction going. That's not a spontaneous process. Adding energy to a system is not spontaneous. You've got to put in some work to do that. Okay, so that's shown by the positive delta H, endothermic positive delta H. And look what happens when delta S is negative. So you get more ordered. Those 2 are going to be non-spontaneous. When you have to pump in energy to a system and you get something more ordered, those are 2 non-spontaneous processes. And indeed, that's what happens. The negative of delta S and then the negative here makes that whole thing a positive. Okay, the positive in delta H also is a positive. Delta G has got to be positive. There's no way around it. So there is no temperature by which you can make that process spontaneous. There is no temperature. There is no condition to make that thing spontaneous. It'll always be non-spontaneous. Now let's take a look at the example in which temperature does control the spontaneity. Okay, let's take a look at the example in which temperature does control the spontaneity. So let's say that delta H is negative. That means it's releasing energy. It's spontaneous with respect to enthalpy, but delta S is negative. So it's not spontaneous with respect to chaos, entropy. Well, at low temperature, this term is negligible. This term is the important term. Enthalpy is the important term at low temperature. That means that at low temperature, this process is spontaneous. Okay, it's spontaneous because delta H is basically the dominant factor at low temperature. That's an example of that is the process of water freezing. Water freezing, water freezing is an exothermic process. Why? Because when you have a liquid going to a solid, energy has to be released. Okay, energy has to be released from the liquid in order to slow it down. And then when you go from a liquid to a solid, there's more order there. It's spontaneous at low temperature. It's not spontaneous at high temperature. When you get below 0 degrees Celsius, it's spontaneous. When you get above 0 degrees Celsius, it's not spontaneous. Okay, so let's take a look at the non-spontaneous process. The non-spontaneous process is this right here. Still negative because we're still looking at the water freezing, liquid water freezing. It's still negative with entropy, but now we're raising the temperature. If we raise the temperature, T now makes this value a lot bigger, and the negative in front of that makes that a negative, and the negative makes that a positive sign. And the positive, if this term now becomes the dominant term, it's going to override the enthalpy term. It becomes non-spontaneous. Water will not freeze at room temperature. Okay, water will not freeze at room temperature. These are important concepts because you don't need hardcore numbers to make these predictions. All you've got to do is think about whether it's releasing energy or absorbing energy. You need to think about chaos, the degree of order. And then you can make the prediction whether it's a spontaneous process, non-spontaneous process at any temperature, or whether it's temperature dependent. Okay, let's take a look at the last set. The last set is delta H positive, and that means it's endothermic. So you might think in terms of, let's say, liquid going to a gas, okay, water going to a gas. When water goes to gas, that's an endothermic because you got to pump in energy for the water to boil it, to make it a steam. And then it's positive as well because gas is greater entropy than the liquid, okay? So it's going to be positive as well, but at low temperature, the enthalpy factor is going to be the dominant factor. That means that you need, at low enough temperature, the liquid does not spontaneously boil. It's not spontaneous. But if you raise the temperature, then what happens is that this term now becomes the dominant term, and a positive and a negative in front of that makes this term more dominant. The negative overwhelms the positive of delta H, and now that becomes a spontaneous process. Delta G becomes negative. So indeed, if you raise the temperature from like 70 degrees Celsius to maybe 300 degrees or 120 degrees Celsius, then water starts boiling, assuming, of course, you're at 1 atmosphere. It becomes a spontaneous process. So this right here is a good case study of how to determine whether your system is spontaneous or not. Some system, no matter what the temperature, will always be spontaneous. Some system, no matter the temperature, will never be spontaneous. Some system, it depends on the temperature. And you can calculate that temperature by this simple equation, delta H over delta S equals T. That's in Kelvin. Okay, that's in Kelvin. And you got to make sure that both of these have the same unit. Otherwise, you're going to be 1,000 off in your temperature. You don't want to do that. Okay, so this right here is an important factor, because I can say that that concept is tested again in your final. Okay, so let's take a look at this. These are some examples, and I'm not going to work through this. I'm just going to talk about it. Right here, right away, you see N2F4 going to NF2. I give you E right here, so you know that delta H is positive, and you know that it's going from 1 mole of gas to 2 moles of gas, so delta S is positive as well. Okay, just by looking at the equation, you know that delta H is positive because energy is on the reactant side. You also know that delta S is positive because you've got more moles of your product than reactant, and they're both in the gas state. They're both in the gas state. So you guys should be able to make that prediction. So if it's positive and positive, you're going to see that at low temperature, this guy dominates. It's not spontaneous. So this reaction is not spontaneous at low temperature, but at high enough temperature, minus T delta S becomes the dominant term, and then it becomes spontaneous. Then it becomes spontaneous at high enough temperature. So let's take a look at that. These are our value. Let me clear this for you real quick. Okay. So that's exactly what we predicted. And then you can actually calculate the switching temperature. Okay. Here's another example. Here it's exothermic because energy is a product. Let's take a look at, so we know that delta H in this particular case is negative because it's exothermic. Let's take a look at delta S. All of this are for the system now, the reaction of interest. So these are all for the system. Okay, we can see we need to make sure we have a balanced equation. That's always important. This equation is balanced. We've got 1, 3, we've got 4 moles of reactant, we've got 2 moles of product. We can see that it's becoming more ordered. We can say that delta S is negative. Okay, delta S in this particular case is negative because we're going from 4 moles of gas to 2 moles of gas, and they're all in the gas state. Sometimes it's not that clear. Okay, sometimes it's not that clear because you might be going to more moles of gas, but now it's converting to a solid or liquid state. In that case, you actually have to calculate the entropy factor. But for this, we can make that prediction based on our chemistry knowledge. So let's look up the value. These are the values for this particular case. Let me clear this real quick. Okay, and it's spontaneous at low temperature. We should know that already. At high temperature, it's going to be non-spontaneous. Okay, so, and the question is, what is the switching temperature? Switching temperature is basically for this right here. What is the temperature in which it goes from spontaneous to non-spontaneous or non-spontaneous to spontaneous? We take delta H on top. We take delta S on the bottom. Notice they're both negative. If they have opposite signs, if one's negative and one is positive, you've made a mistake because temperature can never be negative. Okay, you can never have a negative absolute temperature. There is no such thing as -1 Kelvin. So you know you made a mistake. Okay, look back at your signs. There's no such thing as a negative temperature. The signs are the same. That means that the answer will be positive. Don't forget to convert joules to kilojoules by dividing by 1,000. Okay, and in that particular case, we find out that the switching temperature is actually 463.5 Kelvin. 463.5 Kelvin. Below this, it's spontaneous. Above this, it's non-spontaneous. So the next set of the discussion, okay, I want to get to equilibrium. Just talks to you about free energy. And why is it called free energy? It's called free energy because there's a price you pay for the energy that you get out from any system. Here, I'm just talking to you about how free energy kind of helps you understand the costs in order to drive a system or the economics of it. I won't go into the details. You guys can read that on your own. It's also written in your textbook. Okay. Here it talks about that free energy, delta G, is an indicator of efficiency. When delta G is negative, it's spontaneous. But if it's a small negative, it's not as efficient as if it's a large negative. Okay, a large negative means it's a more efficient process. And if it's positive, well, it's positive and it can be driven. It tells you how much energy you have to invest to drive that reaction. So that's why thermodynamics is so important in science, because it gives you a lot of reasoning, explanation in terms of whether that system is going to be efficient or not in terms of being carried out. So here we're talking about the efficiency of burning gasoline. You know that burning gasoline is probably one of the most inefficient process. The one that is even worse than that is burning an incandescent bulb. The bulbs that we have prior to the millennium generated more heat than light. Okay, well, gasoline, we only extract 30% of that energy. The rest is wasted in heat. Why do you think we're so into alternative fuel? This right here tells you that no transfer of heat is 100% efficient. Okay, if I take gasoline and I convert that to mechanical energy, I don't get the 100% energy that gasoline provides. This example right here tells you that if I have a fully charged battery and I drain it and then I recharge it with the alternator, that the work done by the alternator is greater than the work done to the starter. And that's because whenever there is a transfer of energy, you always get heat as a byproduct. You're always going to lose a certain amount of energy due to heat. And that's important because that right there is the tax that you pay, the energy tax that you pay in order to transfer one form of energy to the other. Even the fuel that we eat, when we eat carbohydrates and food, we don't convert all that to energy that some of it is used to heat up our body and we lose that. So this discussion right here tells you why transfer of energy is never 100% efficient unless we do it infinitesimally slow. Anyway, you guys can read that. What I want to tell you is that the first law of thermodynamics tells you that energy can either be created or destroyed. We have a certain amount of energy in this universe. We can't create more and we can't destroy it. It's only converted from one form of energy to the other. The second law of thermodynamics, on the other hand, tells us that the entropy of the universe is always increasing. Chaos is always increasing. Okay, so this is a famous saying by some thermodynamic scientists. The law of conservation of energy tells you can't win, you can only break even, and entropy of the universe increasing, you can't even break even. Okay, you're always going to pay a price. Okay, and so this is the physical meaning of free energy. The reason why it's called free energy is because when you look at this equation, delta G equals delta H minus T delta S, and then you solve for delta H. Delta H is the amount of energy that system contains, the amount of energy that is locked in the bonds and the molecule. Okay, basically it's telling you that the energy of the chemical is equal to the free energy plus the price you pay for chaos. Okay, this is the tax that you have to pay, the energy tax that you have to pay in order to convert that internal energy to energy that is useful. That's the only energy that is free, in other words. Okay, when you have a fuel, when you have electricity and you want to convert it to like your air conditioner or something, you have to pay a tax in terms of entropy. That's why it's called free energy, because that's the only part that is free after you paid the tax. So, and it's lost due to heat. It's lost due to heat. Okay. Um, the rest of this just tells you the efficiency, okay, and the how enthalpy can address the energy crisis. This is an interesting stat. We represent about 4.25% of the population, and we consume 18% of the world's energy. This is as of, I think, 2018. Kind of reminds me of the COVID crisis that we have. We represent a very small portion, like probably, yeah, 4.25% of the population, and yet we have the most cases, okay? Something wrong there. Anyway, let me, in the next 10 minutes, okay, talk to you about how free energy is related to equilibrium. And I want to at least get through this part so that for those of you in lab, you can at least look at the activity that we're going to be doing on Wednesday. So we have a beaker of water here. And we already know that the water is not going to boil unless we have a high enough temperature. But yet, if we have a beaker of water and just put it out in our kitchen table, and it's not even 100 degrees out Celsius, it's just 72 degrees Fahrenheit, which is about maybe about 18, 19 degrees Celsius. Yet that water will eventually evaporate. And so the question is, why is that water evaporating even though we just spent a whole hour saying that that's not possible based on thermodynamics? Well, the reason why it's not possible is because we are not under standard state conditions. When we are out at, when you put a beaker of water in the kitchen table, we don't have 298 degrees Kelvin. We don't have 1 atmosphere. It's going to be subtly different depending on what's going on, okay? So let's take a look at that again. We have water going into the gas. What we need to do is we need to put a correction factor because we're not at standard state anymore. This is standard state right there. So the free energy that the water feels at your kitchen table is equal to the free energy at standard state plus a correction term. And what exactly is that correction term? That correction term is RT, natural log P, where P is your mass action expression. That's products over reactant. Okay, that's products over reactant. So that's how we introduce equilibrium into this game. And these are the what the different symbol represents. The free energy of the substance under non-standard state, delta G super zero, standard state conditions, gas constant 8.314, not 0.08206. This is 8.314 because we want the gas constant in terms of joules. T is the absolute temperature, and P is the partial pressure of water. Because remember, in order to do a products over reactant, that's H2O, partial pressure over 1. Why is it over 1? Water is a liquid in the reactant, so it doesn't show up in the mass action expression. Hopefully you guys remember that from equilibrium. Only gas and aqueous are going to be put in the mass action expression. That's why that's the partial pressure of water. Okay, so this is basically the generic form. And products over reactant, if it's not at equilibrium, that's the reaction quotient. So hopefully I'm jarring your memory in terms of what we've already talked about. Okay, and so this is the main equation that you guys need to remember for non-standard state conditions. For non-standard state conditions, the free energy is equal to the free energy under standard state conditions plus a correction term. What is that correction term? RT, 8.314 times the temperature under those conditions times, this is natural log, not log base 10, not log base 10. It's a natural log. Make sure you use that in your calculator, natural log. Q is products over reactant. So if we use that, you can see that if we have 1 atmosphere and we put it in there and we solve for delta G, then what happens is delta G becomes positive 8.59. That's not a spontaneous process. So under 1 atmosphere, 298, it's not a spontaneous process. But suppose we have 100% humidity. So humid out there that what's going to happen? Well, at 100% humidity, there's water molecules out here and water is going into the beaker as fast as it's going out. Partial pressure of water at 100% humidity is 0.0313. And we've plugged that into our equation. You can see that that gives us a free energy of 0. It's actually at equilibrium. It's actually at equilibrium. Now, what happens if we have dry air or less than 100% humidity? Well, if we have less than 100% humidity, so our partial pressure of water is about 5 times 10 to the minus 3. It's not 1 atmosphere. 1 atmosphere would be boiling, but partial pressure of water, not the partial pressure of the atmosphere, partial pressure of water. 5 times 10 minus 3 atmosphere, we plug that in, okay? What do we get? What we get is this right here. We get negative 4.5 kilojoules per mole. That right there is spontaneous. That's why water boils at room temperature, because the partial pressure of water at room temperature is not 1 atmosphere. It's below that. And we don't have 100% humidity, especially in the winters. Okay, so that's an important equation. This just tells you how free energy relates to Q. Okay, this right here is a mnemonic device showing you spontaneous, non-spontaneous with respect to Q and delta G. But really, I wanted to get to this equation right here, and then we're done. That's a generic equation. Now, what happens when delta G equals 0? When delta G is equal to 0, then we're at equilibrium. And when delta G equals 0, this term goes away, and delta G 0 equals minus RT natural log K equilibrium. Because we just said we're at equilibrium, so now Q becomes K equilibrium. So look what happens. We now have another way to calculate free energy standard state. Free energy standard state is equal to minus RT natural log K equilibrium. So we know the equilibrium constant for that process. We can actually calculate the delta G. That's basically what we have right here. Okay? That's basically what we have right there. This is the inverse relationship. So in summary, I won't go through this, actually, okay? I won't go through this. You guys can take a look at that. And that's another, the free energy is really, if you think about it, it's really the second law of thermodynamics, in which the entropy of the universe is always increasing. By the way, I forgot to mention that the third law of thermodynamics, I sort of implied it, but I didn't really state it directly, that the third law of thermodynamics is that a pure crystalline solid, it's got to be pure in its elemental state, and it's got to be in its solid state at absolute zero, has zero entropy. Okay, that's the third law of thermodynamics. It just tells you what we already know about entropy, that it does have a finite scale, it's not relative, and that it, in its pure state at 0 Kelvin, that's minus 273 degrees Celsius, then it's got zero entropy. Okay. Second law of thermodynamics tells you that the entropy of the universe is always increasing. You got to remember, though, that we define a new state function, minus T delta S universe, as the free energy function. And when the free energy function is negative, that's spontaneous because of the minus T delta S. So The second law tells us that spontaneous processes always the entropy of the universe increasing. It's not conserved, in other words, entropy. So in this particular equation, I bring together two equations for free energy. One is RT, natural log K equilibrium, and really comes from this particular equation right here. Okay, comes from this equation right here. And when we are at equilibrium, Q becomes K equilibrium right here. And when we are at equilibrium, delta G equals 0 because it's neither going forward or backwards. But that does not mean that delta G 0, that's this term right here, is equal to 0, only that delta G under that non-standard state condition is 0. Okay, so you got to remember that. So when we set this equal to 0 and solve for delta G super 0, then we have an expression that relates K equilibrium to free energy at standard state conditions. And the inverse of that, of course, is this. If we just take the natural log of both sides, well, actually, we divide by RT. That's why we got this. And then we take the exponent of both sides. It cancels out the natural log, and that's why you have EXP here. But this equation is what you guys will need to know for your lab, because experiment number 7 uses this expression. Basically set up this term right here with delta H minus T delta S. And when we do that, we have this expression. We simplify it by dividing by RT, and we have this. This is the main equation, or this form really right here, in which you guys are going to be graphing in experiment number 7. But it relates equilibrium constant to the thermodynamics parameter. Let me just point out a couple of things about this equation. Remember, this is an equation of a line. In an equation of a line, the slope is constant and the intercept is constant, because it's not going to deviate. Okay, it's a line, it's straight, the slope is constant. You got to remember that. The intercept is going to intersect the y-axis at one point. What does this physically mean via this equation? It means that the entropy right here is independent of temperature. The enthalpy is also independent of temperature. And that's because it's constant. The slope is constant, the intercept is constant. In reality, it's not really independent of temperature, but we do make that assumption in terms of this equation right here. Okay, so please keep that in mind, especially when you're doing experiment number 7, is that the delta H and the delta S are generally going to be constant because you pull that out from your graph, from doing a linear regression. So this right here is just a summary slide of all the things related to thermodynamics and thermochemistry. It just shows you how they're all interrelated. But this right here is the important slide, because it shows you how each of these relationships are going to be related to each other, whether it's delta H minus T delta S, whether it's products minus reactant, whether it's, remember, this is for delta G super 0, delta G minus RT natural log Q, that's just rearranging this equation right here and solving for delta G 0, okay? Or whether we have K equilibrium right there. This next chapter, we will take a look at that relationship, how free energy is related to the electrochemical force, that is the voltage that a reaction will possess. So notice that in this equation, it's negative. So a positive voltage is going to give you a negative free energy. In other words, when we get to chapter 19, in order for electrochemical process to be spontaneous, you're going to need the electrochemical potential E0, the voltage, to be positive.